Oh, is it working? Is it working? Oh yeah, I can hear it. Hello everyone. Thank you for coming to our talk. So we're from Embark. We're 3 people here live, but then we also have Riley remotely joining us on the stream. And yeah, this is the title of our talk, Machine Learning for Believable AI Characters. This is going to be the agenda for the talk. We'll be covering...
We can't see us anymore.
Oh, yeah. Oh no. Oh no, we can't see that.
That's Riley though.
Yeah.
Yep, and now we're back.
Now we're back. All right, so we will be covering physically based animation, grounded language, emotion, and then at the very end show a few experiences using all of the tech that we will be going over. So now over to Nora.
Yes. Hi, I'm Nora. I work as a research engineer at Embark. And I'm going to just introduce a little bit of what we're talking about and what we're aiming to do. So most of you have played games. In games you have characters. Characters are usually there. They create a lively scene. They fill out space. They give you information about the world, their enemies that you fight, and so on. However, doing characters can be quite complicated. So the animation takes time. It's a tedious process. You often need specialized software to do it. And it takes hours to learn how to do it nicely. Scripting is also very time-consuming. If you want to do a rich narrative for your game, then that takes time. It's hard to change as well. And sometimes characters end up feeling mechanical in games. So, I guess a thing that we're aiming to do with our kind of explorations that we're doing currently, we want it to be easy to create characters. We want a creator to be more like a director of a scene. It should feel natural to interact with characters. And we're also aiming to make the characters be aware of their surroundings and act with a certain amount of intent, at least to what it seems for the player. So now I'm going to leave the microphone to Riley, who streamed in, and I hope things will work out. Can I do this? Oh, the clicker is not working for me anymore. Can we have the presentation at the same time as we have the speaker? The speaker. Yes. Riley, you're now on screen.
Great. Thanks, Sara. So I'm Riley. I'm a machine learning research engineer at Embark, and I focus on reinforcement learning and specifically animation. I'm going to be talking about physically based animation today and what that is. And I'm going to later talk about what is our motivation for using physically based animation and how do we create them at Embark and what are some of the challenges that we faced along the way. And before I start, I should mention that this slide and the next slide are from a presentation by my colleague Tom Solberry at NDC 2021. You should check it out if you're interested in the topic. It's a great presentation. And before getting to physically based animation, I think it might be interesting to talk about physically based rendering, as I'm guessing a lot more of you might be familiar with that. Before physically based rendering became popular, shader design and computer graphics were often by what it looked good rather than what was correct. And with physically based rendering, we start by what looks correct, and under that constraints we make game art, and we do this by studying light and energy transmission and how light and different materials react with each other. And physically based animation is essentially the same concept, but for animation. And when we switch doing physically based animation, we treat the characters as robots in a physical world. And we start from joints and motors and the states of the body parts, and we apply forces to move them. Like in this world view, for example, if you don't move by moving your limbs, you push a force to the ground, and the ground pushes a force back to you, causing you to move. And so you might be wondering, why do we use physically based animation? And our main motivation for using this was that as Nora mentioned, animating can be a tedious process and you need a lot of expertise. And we really wanted to automate this process to allow everyone to animate their characters. And the other motivation being, and we as humans are really good at telling how the object around us should move. So when something seems physically impossible, it becomes really noticeable. And for classical animation, especially for non-humanoids, that becomes very noticeable as we mostly go by what looks good and when animating them. And also, I think in my personal opinion, the physicality and interaction that you can see in this clip can also add a lot to the game experience and allow you to create a lot of new sorts of experiences that you couldn't have before. And I think it would be important to show some of the results so you can see why we want to use this. And this is Wasabi. You might have seen Wasabi in one of our blog posts. And just to clarify this video, and we'll be showing on later on, our research efforts at Embark for animation have been into two groups. One that is Wasabi, that focuses on finding what is the maximum quality animation that we can get with a lot of expert fine-tuning. And the focus is on big robots. And then the other one is Moro, which is what I work on, and the focus is on diversity. And I'll explain in a little bit what that exactly means. There are lots of overlaps between the projects, and we share a lot of similarities and the same resources and tools and techniques, but the goal for now is different. But we hope to in the future to have a lot of different diverse characters doing a lot of different things in a lot of environments with a lot of really good quality animations with as little input as needed from the users. And this is Moro, the project that I'm working on, and the motivation for Moro is diversity. And what I mean by diversity is the diversity of the characters and the tasks that they do in these worlds, and also the diversity of the environments that they are in. And that is also with as little input as possible with users that might not be experts. And we want to be able to animate any sort of character that you're seeing here as far as they're physically able to do those movements. And I should mention also that this video is a little bit old, so these characters can have slightly better quality now and can do a little bit more stuff, which I'll show later on. And like what's cool about this, also we can have flying creatures within the same system as well. As far as our physics simulation can support aerodynamic, we can have flying creatures, or as far as the physics is supported, any sort of creature should work under the same system. And how do we do this is using reinforcement learning. And I think a lot of you are probably already familiar with reinforcement learning, but you might know it as conditioning. And that's essentially how we train our dogs or even teach humans. And the basic idea in reinforcement learning is that we should reward the behaviors that we like. And in reinforcement learning, we have two different parts. One is the environment and one is the agent. The environment is the place that we are in, the surroundings. In our case here is this terrain and the hills and the goal that the burger man has here to go to, and the task that it defines it. And the agent is the burger man here that you can see in the picture. And in each time step, the environment sends observations to the agent that describe the state of the environment and the agent. And the policy, which is just a function that gets the observation and outputs the actions, gives out its actions, which in our world are essentially the forces that get applied to the joints of the burger man. And then in return, the environment sends us back a reward that tells us how well we did. And we have an RL algorithm that essentially takes all of this into consideration and our past observations and rewards an action and update our policy in a way that we get more rewards in the next time. And how we do that is basically by some exploration and doing the things that got us good rewards before more, and doing the things that got us less reward less. And usually in most RL research, the part that is focused on is agent, and more specifically the RL algorithm. But what we have spent a lot of time at Embark is working on the environment, as we think it's as an overlooked part. And that brings us to curriculum learning. Is one of the ways that we try to make the environment as good as a learning environment as possible. And this is, again, a concept that we are all familiar with. And it's that if you want to learn a difficult task, we should start by learning the simplest form of it. For example, when we go to school to learn math, we start by very simple concepts like 1 plus 1 is equals 2. And then later on, then we learn more complicated subjects like integral. And we wouldn't have been able to get to lesson C without starting from lesson A and B. And we wanted to apply the same idea to our creatures, essentially. And how we started by going about that was basing a curriculum learning based on a paper by the ETH University and Intel Labs called Quadrupedal Locomotion over Challenging Terrain. And this is a robotics paper. And we have made some changes and improvements, but that's probably a really long topic to go through, so I'll skip over that part. But essentially, our curriculum is made out of a set of discrete particle filters that dynamically change the sampling distribution of the environment parameters. And environment parameters are the things that define the environment. Like here, it could be the terrain, shape of the terrain, it could be gravity, it could be friction, and all sorts of things. And the goal of this particle is to estimate the difficulty of a particular set of parameters. And just like biological agents, we want a difficulty that's challenging enough that we learn something from it, but not so difficult that we don't make any progress in it. And what that looks like in action is a little bit something like this. And as you see here, we start by very easy terrain, and of course the difficulty of these parameters don't stay the same. As the agents get better, the difficulty of these tasks get easier, and then so we have to continually estimate this difficulty, and then we evolve our particles based on this. So, and then the agents also in return get better, kind of creates a feedback loop. So what we essentially see is we start by the simplest form, and then we slowly make the environment more complicated, like that we see here. And it's also important to note that we are using bipeds here to show this because I think they are notoriously hard to train because they're really hard to balance. And I think this shows the curriculum learning quite well. To give you an idea, before curriculum learning, these bipeds were not able to walk on terrains at all, but now they can walk on pretty challenging terrains. And although they fall once in a while, which is understandable given their shape and physicality and how extreme this terrain is, but they still do pretty well in a lot of the different situations, which is a big gain from what we had before. And another thing that we've been exploring is multitask learning, and that's essentially learning multiple tasks as the name implies. And at first we started focusing on by a task of going to somewhere, and then we started extending on it. And in this video here, I'm switching between some of the different tasks, like go to task and turn clockwise and anti-clockwise and stand still with the keywords, and so we can show that the agents are robust to these changes and they can do that on a terrain. And essentially we wanted our characters to be able to do all sorts of things like dance, to be jump, and it's really not useful to just have the characters go to somewhere without interacting with the environment. But this was quite a challenging problem because it's really difficult to define one set of reward for lots of different tasks for all of these creatures. And so, for example, imagine creating a reward function for dancing that works for both humans and goats and birds and also some fantasy creatures. It seems like an impossible task, and there are some fields that avoid this, like inverse reinforcement learning or imitation learning and unsupervised RL, which is something that we've looked into, but the results, and we are going to look more into them, but the result you're seeing is all based on rewards. And this all sounds good, but what are some of the challenges we've had along the ways are that this has taken lots and lots of resources. We've spent a lot of time and expertise and resources into this, and building these platforms from scratch, which is what you have to do at the moment, is quite challenging. And because this is a very difficult problem to solve, we are essentially trying to solve the problem of robotics for object manipulation and locomotion for any arbitrary robot, which is quite challenging and requires quite a complicated setup to solve this problem. And of course, we are a long way from solving that. And this complicated setup can bring its own set of problems as well. It makes it really hard to debug, and it makes it also really hard to develop on top of. And because of this, we've had a lot of interesting issues over the past year and a half of developing this that I put in this video. And a lot of these problems are typical software engineering bugs where things just don't work as expected because of technical problems, or sometimes it's physics problems that the characters get stuck. But sometimes it's not a bug and it's just things being set up incorrectly, like the direction of head on the spur. Or sometimes we just give them a little bit too much power and they start jumping around. But sometimes there is no actual problem. The solution that they find is just not what we expected or wanted. Like this lizard walking like a biped, or this biped walking like a gorilla, which is technically the correct solution, but it's just not what we want and not very useful for a game, maybe. And that's it for me. Thank you for listening.
Hi, I'm Miladi. I'm also a research engineer at Embark, focusing on machine learning and natural language processing. So I'm going to talk a little bit about getting characters to speak in the world. So like Nora mentioned before, our goal is to not have one game that we ship where we've written scripts for every character, and you go up to the character and you press a button, and then you get 3 dialogue options, and then character goes into a decision tree of dialogue. So our goal is that you as a user can drop a character into a world that you've created, and then the character just adapts to that world and adapts to some things that you've decided about the character, like about its personality or its knowledge or something. And then people should be able to just go up to the character, type anything they want to the character, and the character responds, coming up with something on the fly. So that's our overall goal with language. So we want characters, as I said, to engage in unscripted conversations with players and also to react verbally to things that just happen around them. So this is a problem called grounded language, and grounding is like a cognitive process where you link things you say, like conversational acts, to information in the world. So some types of information could be like, what's the relationship between 2 people that are speaking? Where is the conversation taking place? Like, are you in a forest or a castle? What else is going on in the setting? And just basically any other mutual information between 2 speakers. So the sources of grounding can be broken up roughly into 2 spaces: perception, which is how we experience the outer world, so what we perceive about the reality around us, and awareness, which is how we experience our inner world, so self-knowledge. So the challenge with this is that we need to create a language model which is agnostic to these 2 things, because as I said before, the user should be able to tailor what the character is aware of, so the user can tailor the information that the character knows about itself, and then the character should also adapt on the fly to what it perceives. So the solution that we have to find needs to be able to, at runtime, take in what the character perceives and is aware of and generate language. So going back into the awareness part, these are some examples of pieces of information that fit into awareness and things that characters might need to ground their dialogue on. So creators will be able to customize these things when making a character, and then these things can also evolve as the character interacts with the world. And then perception, which again is how characters make sense of the world around them. So that
relates both to things that can be perceived with senses as well as things that can only be conceptualized, like facts about the world or common sense about how the world works. And in this case, the world is any game world that the creator could think of. So it might not operate by the common sense rules of like real life. So again, our language model has to be agnostic to how the world that the character inhabits actually works. So I'll go through kind of like 3 stages of perception and then how we model those technologically. So the first stage of perception is sensory simulation and selection. So we're constantly bombarded by like a bunch of different stimuli, and we have to somehow subconsciously filter which information we're actually taking note of. So from a technical perspective, this involves representing environmental stimuli in the game world in a structured way. And then creating some heuristics, whether they're hard-coded or based on machine learning, that filter that stimuli to serve as proxies for what a character would actually pay attention to and what information we would store in their limited memory. The next stage of perception is organization of the selected stimuli. And from a technical perspective, that has to do with creating a data structure where information is grouped and connected so that their placement makes sense for later use and interpretation. And then the last stage, interpretation, is determining what the information that's now organized in our little mental knowledge base means to me, like a person or a character. How do I feel about it? What do I think about it? And in this case, that relates to self-awareness. So one of the so in this organization stage, like I talked about, it has to do with building a data structure where information is stored in a kind of efficient way, where it can also be where the organization also facilitates later usage. So we represent characters' internal mental map as a knowledge graph, which is just a type of graph that stores interlinked information about entities. And deciding what entities or nodes and what relations or edges a knowledge graph has kind of implies the semantics of the world. And when we build knowledge graphs for the characters' internal knowledge base, we can then use graph traversal techniques to filter the information, condense it, and also translate the information into text for downstream use. And this is important because, as I'll talk about later, we're using these knowledge graphs as an input to language models that expect natural language text as an input. So being able to turn structured knowledge into basically natural language text, which is condensed and organized, is a really important step. So this is one example of just a knowledge graph that I pulled off the internet, just to show kind of what it is. So in this case, the nodes are just like different types of proper nouns, like names of people or like geographical places. And the edges are different types of relationships between those types of entities. So like, okay, I'm this person's friend, or like I live in this place. Yeah, so you can encode a lot of diversity of both relations and edges in this kind of format. Okay, so going back to this 3-stage process of perception, I can briefly describe how we accomplish these things in the character. So in the sensory simulation and selection phase, we just simulate perception by sending raycasts from the character as they move around in the world. So by this, characters kind of detect what objects are nearby, and then they can also retrieve any characteristics of those objects or entities that are made available to the game engine. So whatever we make available to the engine, when those objects are perceived by a character also has access to those characteristics. And with the heuristic filters, it's writing heuristics. And then in the organization phase, the discrete pieces of information about what's perceived are just added to the character's existing knowledge graph. So new information gets added to the place in the knowledge graph where it's automatically linked with whatever existing information the character has about whatever that entity is, or so the interpretation phase is what I'll focus on for the rest of this time. So this is kind of like the interesting phase where we want the character to use that knowledge to, in this case, produce some thoughts or statements or whatever. And this happens implicitly in the language model, which is the model that like decides what the character is going to say at a moment. So yeah, I think the next slide is about that. Okay, so now this is about the part where a character actually comes up with something to say. So just kind of how this problem is formalized is like, okay, let's think about a conversation between two participants where they take turns speaking. So it's a turn-based conversation. So participant 1 speaks first, then participant 2 responds, then participant 1 responds again, and so on and so forth. So at each conversation turn or time step, the character comes up with something to say based on or grounded on 3 things. The first is what the conversation partner said on the previous turn. The second is the knowledge, so that's stuff that we just talked about before, like the knowledge graph. And that's everything the character is aware of and has perceived, so both the internal and the external knowledge. And the third is the conversation history, so any previous conversation turns before conversation turn T, in case either conversational participant refers to something that was said earlier. And this is an example of that. So in this case, let's say the player asks the character, oh, what do you think of that bear? So they both perceive this bear, which is the mutual information of the conversation. The character's knowledge graph contains some perception that there's a teddy bear nearby and the teddy bear is pink. And they're also self-aware that they like the color pink. So then in the interpretation phase, which happens in the language model, they might come up with like, oh, actually, I like this bear. It's a really nice color. So that statement is grounded both on the question and the knowledge. So modeling this as a traditional supervised learning problem where you train a machine learning model to predict some outputs given some inputs, basically the input is those 3 things: message, knowledge, and conversation history, and the output is an utterance. So I'll get into some technical detail here, but if you want to know more or are familiar with NLP, then just feel free to ask me after the talk. But this is a really, really hard supervised learning problem, doing generative dialogue in general. We take advantage of research in sequence-to-sequence language models, which are, I guess, quite cutting edge. So sequence-to-sequence or encoder-decoder models are basically neural networks that read in natural language text and generate natural language text. So the model gets an input text sequence, which could be like a single word, a sentence, or a paragraph, like a newspaper article or something, and then generates some output text sequence depending on what the task is. So like a common task is like take in a newspaper article and generate an appropriate like headline for the article, or take in a sentence in French and translate it to a sentence in English. So these are all pretty canonical NLP problems that can be represented in a sequence-to-sequence problem. Okay, this slide sucks. I'm sorry. I actually was thinking about just skipping this, but I figured like it's quite important to why this approach actually kind of works. This thing would have been impossible a few years ago. It's still very hard and very early on. But basically, it's leveraging something called transfer learning. So that is taking a model, a huge model that's been trained for months on general purpose open source data, and then fine-tuning it for a very specific task with custom data. So these models are usually trained for months, on maybe all of Wikipedia or all of Reddit with an unsupervised task. And that means okay, they're just kind of trained to read some internet text and then predict oh, what's the next word, and you kind of have a natural learning objective that way. And through learning to do this, they pick up, or they learn to encode in their parameters something about grammatical syntax, so how sentences and phrases and paragraphs are formed, as well as some concepts written about in the text, which is kind of they discovered was a really nice side effect or bonus from training this way on all of Wikipedia. They learned something about how concepts in the real world are connected to each other. There's even been papers showing that they learned some type of inference abilities agnostic to the actual concepts just by being trained in this way on so much text from the internet. So these models, having some base level of ability already, kind of enables us to then, with much, much less data, do specific tasks, like our task, where you're predicting something to say based on some knowledge and some conversation history. So we are collecting custom data for this task, but it's a very, very small amount compared to what was previously needed to train any sort of generative text model. So as we said before, the NLP model takes in an input text sequence and outputs another text sequence. So we just kind of manipulate our problem to fit into this paradigm. So we combined the message, the knowledge, and the conversation history into a single text sequence where there are other text markers that delineate the boundaries between each of these three types of information. And then the model generates an utterance, something to say, which is the output text sequence. So in this case, the input is that, and the output is what the character decides to say. And this is also the form that our custom training data takes, which we collect in kind of simulated conversations between a player and a character, where there's some procedurally generated information about a world setting. And in the future, we hope to actually collect this data in the actual game world, and that'll be fun. Okay, so maybe I should pause or. So I said in the beginning that we want characters to, or I'll just go back to the previous slide. So I talked in the beginning about how we want characters to not just respond to players or maybe to even other characters when they're approached with some dialogue. So you go up to a character and say hey, what's up? And they respond to you. But we also want them, as they're walking around the world, to prove that they're aware of the world, but just maybe sometimes reacting to something. Oh, they might walk by another, an enemy or something, and just be oh, I hate that guy. Or it might start raining, and then they're oh my God, no, it's raining. So that is the second task that we're doing on the dialogue side, which is about verbally responding to events. And this is done in pretty much the same way as the previous problem with a sequence-to-sequence model. So when an event, which we model as a change in world state, which we model as a relation being added to the character's knowledge graph or removed from the character's knowledge graph, the character comes up with an utterance based on the event description and the character's knowledge graph, which again includes everything the character has perceived and everything the character is aware of. So an example is oh, the event is this teddy bear caught on fire, and the knowledge is, I like teddy bears. So the character might say oh no, someone help the teddy bear, or something like that. Whereas if the character hates teddy bears as their knowledge, they might just be haha, I'm so happy that it's burning, or something. But okay, this is a little bonus. Since the output of the model is just a text sequence, we're not limited to only predicting an utterance. We actually predict both an utterance and an emotion that fits the utterance, or that fits the scenario. So in this case, we predict like, oh no, someone help that teddy bear, and then a text delimiter, which we've taught the model to generate, and then an emotion. And this is, again, like just an example of how this is actually represented in our data set and how this is actually fed into the model and what comes out of the model. So the model actually generates like these, the word message, then a message, then the word emotion, and then an emotion. Yeah. That was all from me. You'll see some examples later on about characters actually speaking and reacting. It's very, very early research. This problem it's kind of ahead of, I think this is like, in general, in NLP, dialogue is in a very early stage, but I think it shows a lot of promise, and it's going to be super exciting. But yeah, I wouldn't say the characters are very intelligent just yet, but they definitely do show that they're aware of both what you're saying and both what's going on around them. So yeah.
Okay, so one of the keywords in the title of this presentation was believable AI characters. And to us, that kind of means that they're believable in a setting that the player finds them in. So like Miladi talked about grounded language, they are aware of their surrounding and they can react to it. So they're believable in the setting that we put them in. Another thing we use to create believability, or if that's what we want to call it, but is emotions and an emotion model. And I'm going to talk a little bit about it because it relates very strongly to the goals we're exploring, but it does not rely heavily on machine learning, except for what Miladi talked about, predicting the emotion. So in the real world, different people react to things differently. And one of the reasons they react differently to things is because of the emotions or the mood they are in currently. So for example, we can have, so to translate this to a game scenario, we would have maybe an enemy. As a player, we're going to go and fight this enemy. So we're on our way there. But for some reason, the enemy is like extremely sad. He's like very sad. It does not make sense for him to attack because like his best friend just died. He doesn't want to attack. He's sad. He runs away. It's not a typical game scenario that we see these days, but it would be kind of fun to explore that kind of realm of like options in games. And for this reason, we are exploring things using emotions and something called a mood engine. Was there something? Yes. So the mood engine in this case, we're basing it off a model called ALMA, a layered model of effect. And the two main components in ALMA is emotions and mood. And then we can have a layer of personality to that. But I'm mostly going to talk about the emotions and the mood points of this. So the emotions are the things that characters like feel instantaneously. So, for example, in the event model that Miladi talked about, they see an event, they see it, they get an emotion from it. Oh no, the teddy bear is burning, and they get scared. Take that emotion, and we give it a decay function. So after a while, it will go away. You will not be scared anymore. But we want to keep it for a while, because we don't want the character to become scared and then instantly become something else. The mood model, on the other hand, it is a model that has kind of like, it's the average state of emotions. So for example, if our character's been extremely sad for a while, and then it becomes happy, it doesn't make sense for it from just like receiving something they like. They become happy if they're extremely depressed. But they get a little bit happier. And that comes in the mood model. And then we can output this to, for example, facial animations, so that we can actually see what the characters are experiencing internally. So the emotion model that we're using currently is based on the basic 6 emotion. Some of you may recognize it because it's like a very common way that humans perceive emotions. And there's a lot of discussions surrounding emotions, but at least for now, it's one of the models that are these are the emotions that are seen to be universally recognized in human beings. It only uses 6 emotions. Normally, when you do emotion, like a lot of emotion papers use something called Orton and Collins' Clare model for emotion. It has an extreme amount of emotions. Well, at least it's 22, which is way more than 6. And for machine learning models, and especially for like annotating data for machine learning models, 6 is much easier than 22. And this is one of the reasons we're using this. There's also more data sets available on emotions for basic 6 than it is on the Orton and Collins Clare emotions. So here you can see it's happiness. You can see sadness, anger, fear, surprise, and then disgust. And I think these are also commonly used in animation, but someone could probably correct me on that afterwards. So these ties together emotion to animations. We can use these in animations when we're like modeling emotions. Every emotion is also given an intensity. So you can be a little bit happy, or you can be very happy. This is my worst slide. So on the mood side, we have a model called PAD. And PAD stands for pleasure, arousal, and dominance. And that is a framework for modeling emotions in a vector space, where pleasure is a representative of was it a good or bad experience. Happiness, it's good. Anger, it's a negative experience. Arousal, it states how excited or how energetic the state was. Anger is a high energy emotion, while sadness can be very low. Dominance, and dominance here is how controlling the state is. And that might be hard to like understand exactly what it means, but if we take anger and fear, where anger is a high energy negative emotion, fear is also high energy negative emotion. What differs in their cases is that anger is a very controlling emotion in this case, while fear is a submissive emotion, which is why in many cases we add this dominance variable. This is just a list of translating different types of emotions, in this case the Orton and Collins Clare model, into vectors. But we're not going to look at that. We're going to look at my clearly artistic images of emotions instead. But here you can definitely see different states in pad space, where you have an exuberant, it's called, but it's a very happy, excited state. You can have happy feelings, but they're just like more relaxed or dependent liking, this one is called, but yeah. While on the other side, we have bored as the all-time low emotion. The next slide, I'm going to warn you, because this is like some of my early things. I never thought I would show this outside of Embark. But yeah, so this is just showing the engine and how it's working. I'm glad we have artists. So here, just showing, adding emotions. And for those of you who have good eyes, you can see a list of emotions showing up for whenever I give it an emotion. And they decay after a while. In this case, we have a very quick decay, so we can visualize it more easily. So here, just... and this, well, theoretically at least, will give the creatures at least a more natural emotional state. Except when you're looking at my animations. Another thing we can do with emotions is that we can attach a reason to why they have the emotion. So, for example, in the case of the event, again, where the teddy bear is caught on fire and they get fear, we can also save the reason. Well, the teddy bear caught on fire, that's why I'm scared. To the emotion, which we store for at least a certain amount of time. And in this way, the characters can tell a player why they're feeling a certain way. So now we'll see some of both the language model in use and also this storing of reasons. Do we have audio on this? So in this case, we have a seal. And as you could see, it was way too quick, actually, but it's like, I like cones. So it became like a little bit happier from getting this cone. And now it's like, oh, I'm extremely happy because I came near cone. And then I can actually ask it, why are you happy? I came near a few cone. And this is all the language model generating the responses. And I'm going to leave it at that. Oh, can I go back?
You can just play.
Okay, and give it to Sara.
All right, thank you, Nora. All right, so we're at the end of the presentation now, so I figured I would just show some examples of the tech that my colleagues have been talking about and how it can look when you put it together as an experience. So let's start with this one. So here I've just made a kind of scene with some characters, and I've set up some game rules, basically. So here, if I give the strawberry to this salamander will walk over to a target, and the targets are these flowers over there. So it is walking, using the train locomotion that Riley was talking about earlier. So like I haven't given it any pathfinding, nothing like that. It's just walking over to its target. And it's reacting to the targets as well. I've also set some rules that if it's near these targets, the flowers, it will consume them. And so now I'm asking it what it just ate, and it is telling me purple flower. You just couldn't see my little, what did you just eat, because it hit it for some reason. And here we have a test of just putting together gameplay sequences and the player interacting with things in the world and characters reacting to them. And so it's telling me, oh, you can bring this bag of seeds over to the garden. So I'm like, okay, let's go find the garden. I am bringing bag of seed over to the garden. There's a garden here. Drops bags of seeds. Nothing happens. Okay, I need to figure out what to do next. Because I made this, I know exactly what to do. This little puzzle, and so I picked up this shovel. Now this lister is telling me I really need that. It's reacting to the fact that I gave it a shovel. And I have a rule that if it's holding the shovel, it will walk over to the garden. So that's what it's doing right now, and it's walking on this terrain. And also I have a rule, if it's close to grass, it will eat the grass. Doesn't like the shovel, drops it. That's just a preference. And now I'm walking back into the forest here. Grabbing some mushrooms because I know that there's a character here who really likes mushrooms. So I'm going to walk over to this character and give it what it likes. Yeah, grab the mushroom. And I have a rule set that if this character's happy, it will start raining. And I really needed the rain to grow on this garden so I could get this pumpkin to grow from the bag of seeds. And what I'll do with this pumpkin is irrelevant, you will see soon, but I will bring it over here to these logs. Everything makes so much sense, I know. I also do know that the burger man doesn't like mushrooms. Oh, hey, salamander with a broken tail. So I will bring it over a mushroom to the burger man. I don't like rock. Okay, well, I also know you don't like mushrooms. Oh, it's getting disgusted by these mushrooms. I have a rule that if the burger man is disgusted, the logs will get set on fire. Because that makes sense. And I also have a rule that if the small pumpkin is near anything that's burning, it will turn into a cake. So we have this cake, and earlier the puppy told me, bring me cake. So now I am bringing you cake, exactly what I needed. Thank you. And here we have a scene that Miladi made. So super cozy scene where she set up like a kind of a semi-experience. So not so much that I have to solve a puzzle, but it's more about characters living and reacting to their surroundings. And they do have some tasks. So she set up some rules that, for example, the seal walks between 2 different locations to pick up some pearls and bring them over. And that's what they're doing. And they're also, like walking around, reacting to things, saying hello to the tree trunk. You feel better now. That's great to know. Look, a pearl, because it was looking for a pearl and it found it. Now it grabbed it and it will walk over to drop the pearl somewhere else. And so this is, you could call this, I guess, like a little diorama. You can just go in here, hang out. You could talk to them if you want. So I just stopped because they wanted to talk to me. Nice to see you. That's very pleasant to go into a world and just have a cute little salamander say nice to see you. I would love that. But those are very, like, I wouldn't say scripted, but like very, very planned sort of experiences. But what's really exciting about this is all the unpredictable, all the surprising like reactions that happen. So you can chat to characters or they react to things. For example, someone asks, are you in love with me, to this lizard? No, I am not. I am in love with Alex and Ferruccio. It's like, well, thanks. Or like, I just went up to this seal and asked, hello. Or I think I literally just said hello and it said, I am Seal. I don't know who you are, but we are in love. It's like instant connections with these characters. I'm forming bonds. And I mean, like, just so cute that, serotonin is my nickname. So it's like, aha, I'm in touch with serotonin, or like, yay, I'm so close to you. It just like, it just brings me warmth. It's so cute. And then one character there is asking, I wonder what Elsie is up to, probably because they're friends. There's also some janky stuff. I mean, this salamander that we saw earlier deciding that it wants to become a fox and jumps into the ground and gets stuck because physics. And like the way that the puppy picks up the cake is also very funny because we have an attachment point at the root of the body and it happens to be the mouth. And then also the burger man being put in a cauldron and reacting looks like a nice place. Well, I'm glad that you think that. And also here, the face that is attached to the body grew because of some rules that we put in and the rest of the body just stayed small. Like these are just, little funny, memeable moments that I hope that players will just enjoy and have fun with. And that is all for us. Thank you so much for listening to our talk. And if there's any questions, please go ahead.
I can get some. Yeah, there I am. We have lots of questions. However, we do not have a lot of time. But I'm thinking a couple of you might be heading over to the afterwork. Yes. And a couple of you might be heading over to the afterwork. So I hope we can do some of it there as well. But I just have one question, and I think maybe some people are thinking that as well. Like, how does this affect the way that the animators and the actors, voice actors, for instance, how does that affect them in the future? Because now we have a completely new way of working, I suppose, when a lot of it is being AI animated.
I think the target experiences are very different from what like a well-trained professional animator and like a trained story writer creates versus what is automated through machine learning. So like what we have shown here, it's funny, it's janky, it works in some way, but it's like a silly experience for you to like casually create something or casually interact with something versus like a very fine-tuned like beautiful game where every character has like a very nice gait, and the story makes total sense when they talk about it. So I just think that it's a different tool set.
It's a different tool set, yeah. And then you don't think it's going to be completely changing the business that way. It's going to be two different ways of approaching game
I would say not for a very, very, very long time, if ever.
And I think like one thing is it's going to change maybe the business in the way that anyone can use it.
Exactly.
Wonderful. Well, we're gonna actually draw a line there to make sure that we don't, and we're gonna say thank you to everyone who joined us. It was very inspiring talk, and I'm sure that lots of people are gonna try to catch you now on the way out. And we're gonna say thank you everybody for keeping us company all day. It's been an amazing experience, and it's been really, really cool meeting up with you. I also want to say thank you to everyone joining us online this afternoon, and I hope to see you in person next year. Thank you, everybody.